Hello everybody, I'm Cash Merrill and this is my Exam 1 video for the write-on portion. So let's go ahead and get started. So question 1 was about the characteristics in the flowers, and letter A wanted us to come up with a null hypothesis. So my null hypothesis was that I believed that the purple color for flower color was dominant to red, and that long pollen was dominant to round, and that these two traits followed Mendel's laws of independent assortment and the law of segregation. So I always knew that our parental cross was a homozygous dominant for both, crossed with a homozygous recessive for both, which gave us a heterozygous F1 generation for both traits. So when those two were crossed, my predicted ratio was a 9 to 3 to 3 to 1, so it'd be 180, 60, 60, and 20. So when I used those numbers with my observed in the chi-squared test, I went observed minus expected squared divided by expected and added those all together here. My chi-squared value was 168.53 with 3 degrees of freedom. So that was well out of the range that it needed to be in the table of chi-squared values. So for C, I rejected my null hypothesis. Now my new hypothesis, I still believe that purple is dominant to red and long is dominant to round because of the F1 generation that it told me that was produced. But my new hypothesis was that these traits follow a form of non-Mendelian inheritance with a ratio. Specifically, my new hypothesis was 11 to 1 to 1 to 3. So with that new ratio in my F2 generation, I would expect 220 purple long, 20 purple round, 20 red long, and 60 red round. And if you just look at the values, that would be a lot closer for that. So that was my new hypothesis. Let's get a move forward. So number 2 was talking about Huntington disease, which is a dominant disease allele. So letter A was saying, what is the probability of all 6 of these children being affected? So it was a cross between a homozygous recessive male who didn't have the disease and a heterozygous female before her onset, but she has the disease allele. So we can see that 1/2 probability is that of having a child with the disease. So 1/2 to raise to the 6th power for 6 kids gives us a 1/64 or a 1.56 chance of that happening. Letter B is, what is the probability that 4 children will be unaffected and 2 will be affected? So it's asking us 4 and 2 without a specific order that this has to happen in. So we're going to use the binomial expansion equation. So we have 6 factorial, the total number of outcomes, divided by 4 factorial, those who will be unaffected, times 2 factorial, those who will be affected, times 1/2 the probability of those unaffected raised to the 4th power, number of that happening, times 1/2 the probability of being affected raised to 2, the number of events that we want that to happen. And when we do the math for this, I got 23.44% that 4 would be unaffected and 2 would be affected. Now letter C, it's asking, what is the probability that the first 3 children will be either all affected with Huntington disease or all unaffected? So we know already that this is going to be a sum problem because of the word or. But it's a 1/2 probability of being affected, so 1/2 times 3 children, 1/2 times 1/2 times 1/2 gives us 1/8. Same 1/2 probability of not being affected, so 1/2 times 1/2 times 1/2 is 1/8. Add those two probabilities together, and you get 1/4 or 25% probability of that happening. Now number 3 was our pedigree chart question. So letter A, I drew the pedigree charts up here. So letter A I got was X-linked dominant. So when I first looked at this, I saw that the disease is in every generation, so it does not skip generations. Both males and females have it, but the key here is if we look at these 2 males that are affected, only their daughters receive the disease and are affected, but their sons do not. So the dads always pass that X allele to their daughters, but they do their Y to their sons, so only the daughters received the disease. Now B, right here, I got was autosomal dominant. And again, I looked and saw that it doesn't skip generations. Both males and females have it, but the key here for me was this son right here who has the disease or the allele. got it from his dad right here. So it can't be X-linked dominant, so it must be autosomal dominant. Now for number 3, letter C, I got that it was X-linked recessive. And that's because we can see it skips generations, and at first you see only males are affected with the disease. And so we can see that this mother was a carrier here, and this mother was a carrier here. So that only happens with X-linked recessive, that the son only has like one X chromosome, so he's going to display the phenotype. So that one was X-linked recessive. D, I got, was X-linked dominant. And it's very similar to letter A, of course, that we can see that this dad was affected. So all of his daughters were affected and none of his sons. This female was affected, and she had about half and half sons and daughters affected because she can give the X to a son or a daughter. But this dad can only give it to his daughters, so therefore it was X-linked dominant. Now number 4, mostly you kind of have to just think about it in your head. It's talking about the number of chromosomes in the African hedgehog. And so the African hedgehog has 90 chromosomes in a typical diploid somatic cell. So then it asks how many sets of chromosomes. So we know that we get a set from our mom and a set from our dad. So I just went 90 divided by 2 is 45. So this African hedgehog would have 2 sets of 45 chromosomes per somatic cell. Now number B, the letter B, is asking us how many tetrads are found during prophase 1. So during prophase 1, we know that's when the chromosomes, so before prophase, we have S phase where the chromosome duplicates. So each one of these separate chromosomes duplicates and becomes 2 sister chromatids. Then in prophase 1, we know that they come together to synapse and form the tetrads. They won't necessarily be like this is more like metaphase, but they'll be together. And so since there are 45 chromosomes from mom, 45 chromosomes from dad, and those two each line up as tetrads, mom, dad, mom, dad, mom, dad, then he will have 45 tetrads during prophase 1. Then letter C asks how many sister chromatids are found during metaphase 2. So during anaphase 1, this side's going to go into one cell, and this side's going to go into one cell. And so then you end up with just one of the columns here. So these essentially split in half. So here you would have 180, or 80 sister chromatids, but now in metaphase 2 you're going to have 90 sister chromatids, so the answer is 90. Letter D, how many chromosomes are found per cell during prophase 2? So like I said here, these are going to split during anaphase 1. So in prophase 2, you're going to have half of these, so just one column, so you're going to have 45 chromosomes. The African hedgehog will have 45 chromosomes during prophase 2. Now number 5 is asking of us about a tetrahybrid cross. So I went ahead, when it gave me the 2 parents, I went ahead and did a Punnett square for each of their alleles here to kind of get started on the problem. So first it asks, what is the probability that a dwarf, which is homozygous recessive for that, so 1/4, a dwarf, wrinkled, also homozygous recessive, 1/4, a yellow, which is in this case, you can only have heterozygous, so it's 1/2 probability, and a terminal, which is also 1/2 probability in the A's right here, the homozygous recessive, will be produced. So if you multiply all those probabilities from each Punnett square together, you end up with 1/64 or 1.56% of that happening. Letter B is asking us what is the probability of a specific genotype, specifically this one right here. So they want heterozygous for the T's, so that's a 1/2 probability, we can see from our square. Heterozygous for R's is also 1/2 probability. Heterozygous for Y's is a 1/2 probability. And heterozygous for A was a 1/2 probability. So you multiply all those together and we get a 1/16 or a 6.25% chance of that happening. Now letter C is what is the probability of the first 5 children having this specific genotype right here. So homozygous dominant for T's is a 1/4 probability. Homozygous recessive for R's is a 1/4 probability. Heterozygous for Y's, we already know, is a 1/2 probability. And homozygous recessive for A's is a 1/2 probability. Multiply all those together and you get a 1/64. But it wants to know what is the chance that the first 5 offspring have that. So now you take 1 divided by 64 raised to the 5th power for 5 children, and you end up with a very small probability of 9.38 times 10 to the negative 8%. So obviously a very low probability event of that happening. Now, letter D, what is the probability that an offspring will have the dwarf round yellow axial phenotype or the dwarf wrinkled green terminal phenotype? So now we need to find the probability of each of those events happening and then add them together because it's the same or. So it's an addition problem. So for the dwarf round yellow axial, so dwarf is 1/4 probability, round is 3/4 probability, yellow is a half, and axial is a half. Multiply those together, you get 3/64. Now for the next one, dwarf is 1/4 again, wrinkled is 1/4, green is a half, and terminal is a half. And that gives us 1/64. So you add 1/64 and 3/64 together, and you get 4/64, or 1/16, or 6.25%. So that's how I did the problems for the exam 1 write-on. Thank you for watching.